Okay, hello everyone out there who are watching and listening to today's talks. This talk is about testing WebAssembly in relation to the project Alex was mentioning before. The original title was Weird Quirks about that, but I think in the end I ended up on a more positive side of the things. And yeah, try to do a quick journey about what I have learned about that. So my name is Pawel Bylica. I work for Ethereum Foundation for long years, and I'm mostly doing stuff related to EVM, Ethereum virtual machine. So I'm maintaining some existing code for that and also doing research and evaluation of proposals to change how EVM works. I was also working for eWASM project, which the main goal was to introduce WebAssembly to Ethereum blockchain, previously as a replacement for EVM, and then we thought about running them side by side. And currently, we did change a name to the team that was working on execution engines, and the current name is Epsilon, which Alex mentioned before, and you can find some of our notes on the site linked there. So this talk will be related to the project presented before called Fizzy, which is WebAssembly interpreter written in C++, focused mostly on speed and compliance to the specification. And one of the goals we had with the project was to evaluate and improve WebAssembly 1.0 specification. That wasn't the only goal, but I think this talk is most related to this one, and I will try to explain that in 3 different parts. But first of all, we need to answer the question what actually we mean by the WebAssembly 1.0. So I think the most correct answer to that, what it is the document that is published under name WebAssembly core specification, done in December 2019, and this is official W3C recommendation, and you can find it on this link. So that's purely WebAssembly specification text. You can read that, but there's some things missing. And there's also second source you can look into. This is a GitHub organization, the GitHub organization WebAssembly that has a repository called Spec, and this source is I think much more useful because addition to the text, which is regularly published in automatic way of the specification, you can also have, and it contains also specification test, so-called WAST files, and WebAssembly interpreter implementation in OCaml, which is change aligned to the specification changes. So these are 2 important parts of that. But the problem we had with this repository, it doesn't clearly mark the 1.0 version. So there are different Git tags and different Git branches that kind of suggest this is work related to 1.0. But we weren't 100% sure that we actually have the correct one. So we believe the branch mentioned, the last one, is the correct. Although we also had issues with building the final document that is published on W3C webpage. But nevertheless, we continued our work from this W3C 1.0 branch, which is still there. And why I'm mentioning continuing working, because so what we wanted to do is to improve WebAssembly by contributing to the specification. And first of all, we identified missing test cases and wanted to submit new ones. And but we by the design we want our product to be restricted to WebAssembly 1.0. So we don't really want to use spec tests from, let's say, master branch, where there are some extensions added and it tracks what is called WebAssembly 1.1, although this version never has been finalized yet. So that's not really an option for us. And additionally, there are some issues to the spec that would welcome some corrections. They are not like substantial problems, but we've seen some small corrections happening on the way, and they are not included in the 1.0 document. So one example of such like small bug fixes, I just found it when I searched that recently. It's done by some other contributor, and it mostly fixes a typo, but it's like it makes the specification more correct and less confusing this way. So there's, in this case, and it affects the load instruction, which is definitely part of 1.0 specification. So I double checked that, and in the master, or like the recent specification published regularly, the change can be seen, and in the W3C specification, this change is not there. So because like of these two problems, mostly because not having any maintained 1.0 branch for WebAssembly specification, we decided to do it ourselves. So we have the fork of the spec repo, and then we created the branch, which is W3C 1.0 test backported. Originally, we mostly considered test backporting to that, but there are also like small fixes also included. We also had some discussion with the maintainers of the spec repo, but I think that hasn't been resolved fully. And the interest in that, I'm not sure. Like to my impression, was like limited. So yeah, I think that was needed for our job, and we started to do that. However, there's this one issue with the process. How does it work? So we prefer to at least the new test additions to be first included in the upstream spec repository, but the only option to include them is to target the master branch of that. So that's sometimes challenging because of the additional extension that already exists there. And only after this change is, the test set is accepted upstream, we can backport that to our branch. So it also kind of prolongs the process we follow. About the new test additions. So besides like manual discovered like cases we would like to add, which is rather rarely, we had two big sources of the possible test cases. One is fuzzing and second is code coverage. And I will try to quickly go through both of these sources. So for fuzzing, I actually mean WebAssembly validation fuzzing. Quickly introducing fuzz testing. It's a like semi-automated process that generates pseudo-random inputs for your code, and then it expects some feedback loop to if the generated input are interesting or not. The most famous feedbacks is if your program crashes. That's like great because the fuzzer is super happy about that. But there's other options to provide some feedback information to this testing. And in case of WebAssembly validation, that's ideal and also simple case. It's because of the like structure of validation. So as an input, you get some binary data. So it's mostly the array of bytes, and that's exactly what the fuzzing tools are generating. And as the output, we actually have like only one bit, which very much limits the size of that, because we only get information if the provided bytes are a valid WebAssembly module or not. So in particular, in our case, we used, because most of the code we did test is C or C++, we used LeapFuzzer, which is part of LLVM toolchain, along with the LLVM sanitizers, and there we used less known, at least, additional instrumentation options and runtime options to extend number of checks the sanitizers are performing, especially for our code. I didn't list all of these, but if you may be interested in this, there's a way to find that in our repository in the configuration files, or I can answer some other time about that. And the main targets were Fizzy, our project, and Wabbit mentioned before. Wabbit is is a WebAssembly binary toolkit, which can serialize, deserialize, validate, and also interpret WebAssembly code. And also resides in the WebAssembly GitHub organization. And how exactly that was, well, the testing loop, how it looked like. So as you can imagine, the first step is to actually feed the bytes to Fizzy or and Wabbit and compare the answer. If they agree about that, about the validity of some bytes, that's great, and we can like check on our test case. And in case it happens that one of them, if in case of mismatch in their answer, that's a hit for us, that something is wrong in some of them. So what we can do with that, with this dump of the test case, we can convert that to more representative form, which is WAST test. It's not super complicated, but it needs some additional annotations, what you expect from it to be. But mostly it's done to actually feed it to existing other tools. And then we confront that test case with the mentioned before spec interpreter, which is this OCaml implementation of WebAssembly, and then we can know which one was right about that. And finally, we can debug the one which is was fault, and that was mostly Wabbit, and it's not because it was badly implemented, but there are some reasons for it, and I will explain that later. So then what we can do is to debug and fix the code, or at least report the issue in the upstream project. We usually go with the fix because it wasn't so difficult to do with that way. And like having some confirmation from people working on different projects that this is something worth fixing, we usually upstream the tests to the official spec repo. And finally, we can backport that to our WebAssembly 1.0 branch. That's mostly how it looks, and we can repeat that over and over again. Yeah. And side note for that, we did publish the exact so-called fuzzy corpus, which is the collection of all of the test cases that the fuzzing tool finds interesting in both of implementations. The cases are not really long for reason that this process hasn't been finished yet, and so we mostly limited the number of the size of the input to make the testing faster. And you can find additional information in the link about that. So to summarize this fuzzing effort, it's not completed because after extending the fuzzing, mostly the input size, we discover new issues, and there's like it's quite time consuming to fix these all the problems in this single point in time. So this is ongoing process. Hopefully it can be also taken and continued by someone else, and most of the issues we found are related to first of all custom sections that can happen in WebAssembly. So in our implementation we ignore them because we don't have any interest in them. But it happens to that some of the custom sections are actually specified in some other places, and they also have some validity rules. So Wabbit understands some of them. That means it will also validate custom sections if they happen to find them. And this is one of the reasons Fizzy and Wabbit are in disagreement about some of the modules. Meaning that Fizzy will consider them valid and Wabbit not, because some of the custom sections are actually not valid. So for us, there's not really other way to kind of add some ignore list to the tool to ignore such errors. It's a bit of annoying part, but can be solved. A second, and like the biggest source of issues in Wabbit was actually other extensions. So Wabbit doesn't enable these extensions by default. At least that was the case some time ago. But at least all the tools they provide have an option to disable or enable an extension. However, they are not really very precise about that. So most of the cases, the binary loader or parser, called differently, actually was too permissive about some of the things coming from extensions and allowed that to go further. And that was to my if I recall correctly, the main source of the issues. And yeah, and we were able to correct these one by one. And something we haven't done, but I think it would be even more exciting than the validity fuzzing was to actually execute some code and check if both produce the same results. So we planned to do this. As always, there's little time to do stuff, but yeah, if someone is interested, that would be interesting project, I think. And one thing we found would be mostly required for it is some kind of metering to at least cap how long the WASM code executes. Otherwise, you can quickly find infinite loops in the code, which is valid, and but yeah, will halt your fuzzing efforts. Okay, so that was more or less about how we did fuzzing, and this another source we used for feeding new test cases to the official spec, which is code coverage. Even if in this example, which is just by one thing is kind of just catchy image, you can see that this is the part of physics code, nothing you should really read about, but in what we identified that the official spec tests are more or less optimistic. So what they do most of the time, they kind of assess if the positive aspect of something happened. I mean, mostly if the execution or anything else happened the way it was designed for, but they don't really check all the cases when WebAssembly should fail in a specific way. So that's actually easy to find in the code coverage traces, because error cases are usually, I mean, some of the error cases are not covered by that. So we put a bit of attention to this, and we separate test coverage reports by the tests that we are running. So for internal unit tests, we do have separate report. And for official spec tests, we have additional report. And then we can see in this additional report that which lines in the code of our implementation are not covered by that. Yeah, and that was like pretty straightforward way to extend number of spec tests upstream. I think we didn't cover all of the cases yet. The example from the previous site was actually taken from the most recent test coverage report. But this is relatively straightforward process. And you can repeat that over and over again until you reach 100% coverage. Yeah, now I'm coming to the kind of the last subject of this talk, which is floating point instructions in WebAssembly. So if you recall, I mean, there's one bit of information I will need later. Well, there's a lot of to say about floating points, but one thing I will need later is that you can decompose such representation, floating point representation, as a sign bit, exponent part, and mantissa part. And yeah, let's move on. So so we did consider starting a Fizzy project and also WebAssembly project as a whole. I mean, eWasm project as a whole, to skip floating point instructions altogether. So first of all, we don't believe they are super critical to implement blockchain programs or smart contracts. So that on its own can save us over 60 less instructions to implement and to test and to maintain and to do all the stuff that is related. I mean, it's also like limits the attack surface and all other properties of the system. But most importantly, the floating point specification for WebAssembly allows the operation to be non-deterministic, and that's like critical part. So we like the initial goal was to implement Fizzy interpreter without any floating point instructions at all, and that was the first version we had, and we're super happy about that. But it actually turned out it's not really practical implementation for mostly two reasons. First of all, the official spec tests are not really designed the way you can skip floating point instructions. I think nobody thought about that useful thing. So floating point instructions are mixed in for testing of different aspects of WebAssembly. For example, you can find big test suites for memory in WebAssembly that just use floating points because they need to pick any type for some tests, and it's not there doesn't exist easy way to avoid floating point instructions unless you want to skip a lot of spec tests from running in your program. And lastly, there's also like a lot to explain to other people and other projects that you don't support this part of WebAssembly specification. So I think we quickly realized that I think it's just easier to implement floating point instructions and move on. And that's what we did. So, I mean, the most complicated part of that is maybe not the most one, but the thing that was one of the reasons we didn't want to have floating point instructions is a non-deterministic aspect of theirs, and but actually the good news about that. So they are only not deterministics around nonce, which are the special values, meaning not a number. And if you can recall from the previous slides, when we had these three different part of representation of floating point, nonce are the values that has all bits set in the exponent part, and at least one bit set in the mantissa part. So WebAssembly specification allows the sign bit of none value to be non-deterministic. So if an instruction should result in having in a none value, it can give you any sign it wants, and that's fine according to the spec. And also can put you any bits in the none payload, which is stored in the mantissa part. But there are some additional restrictions to the last thing. So if we would expect these payloads, so we have the two main categories for nonce. First one is arithmetic, which is also called quiet none in some other specifications outside of WebAssembly. And there are also signaling nonce. The difference is that the first bit of quiet none is always set to 1, and the signaling one is always set to 0. So signaling none has to have some other bit set to 1. The point here is that WebAssembly disallowed to returning signaling nonce as a result of any operation. And the special arithmetic none, which is canonical, is called in the spec canonical, and it only has the first bit set, and all other bits are set to 0. And if we can examine like how the specification for that works, I tried to summarize on this, let's say, set of semi equations. But mostly the rule is that if you have some inputs to the floating point instruction, and it only has real normal values that are non-none values, and some of them are canonical nonce, they must stay as a canonical none, although the sign bit might change. And only if you have some other nonce being the input, this is the fourth of this, the result may be an arithmetic none. So there is no way to produce signaling none here. That's one important part. And as long as they operate on canonical nonce, you must return some kind of, canonical none with the with some of the either positive or negative one. So the quickest, the simplest and also, in my opinion, elegant way of adding determinism to floating point instructions is to always return canonical none. In case the instruction must return some none value. That's fully conformant to the specification, because canonical none is also one example of arithmetic nonce. The only thing about that is that there might be different way of handling determinism, which is more performant. In our case, that would mean we need to check all the results of the instruction. So if happen your hardware produced a none value, you need to replace the none value with canonical none value. So yeah, so that was our idea how to like solve non-determinism issue with the floating point. But we also spent a lot of time to understand all the quirks and problems that floating point numbers are famous for. So something Alex mentioned before, we integrated to our testing framework was a soft float implementation. This is project I think hosted on Berkeley. There are actually two projects. One is called soft float, and the second related sister is test float. I don't believe they are distributed in common Linux distributions or any places, but they are relatively easy to build on your own. And the TestFloat project contains a tool called TestFloat Gen, which takes the instruction, the type and the instruction as an input, and some other options. You can inspect that on your own. And for that case, it generates quite substantial number of test cases with the expected results. All of them are output in hex form, matching binary representation, and there are also additional information as the expected exceptions happening and other bits of information. But the point is, you can precisely parse these test cases and confront your implementation with what the TestFloat product expects. And this is what we did. We built a custom tool which is relatively simple. It has two main features. First of all, it takes these specific TestFloat inputs and process them to create internal tests. And for internal tests, it also generates a very simple WebAssembly program that uses this particular instruction. Then we feed this WASM module with all of the test cases provided by TestFloat, and we check we got the right results. So some discoveries we had during this testing. We actually started with the most common architecture, which is x86 64-bit version, and it actually matches the SoftFloat implementation quite precisely. So none values are not really specified in the floating point specification, none in the WebAssembly specification. I mean, the precise payloads that you expect, but SoftFloat matches what this architecture generates. Maybe that's the other way around. I didn't investigate that fully, but we were kind of happy what we had. So we also extended test for non-payloads to make sure like they stay as we wanted them, and we were quite happy. Can we go back one slide, please? But there are some issues we discovered with this already. So WebAssembly and also like all the compilers we know actually doesn't pay so much attention to non-values, and propagating non-values for instructions that are like mathematically commutative, like addition, multiplication, and so on, actually means that if you provide some non-values as an inputs, the order actually matches. And compilers heavily disagree with us, so they're happy to swap the operands in the code in which order they actually feed it to the instruction. So we already had some issues for that. I mean, it still stays with the WebAssembly conformance, but at least depending on the build options and without these deterministic floating point instructions, you actually may get different results in your program. So that was the first discovery. Secondly, we moved to ARM. I don't remember a lot of details about that, but at least the non-payloads start mismatch with the SoftFloat produces. That's still fine in terms of WebAssembly specification, but we already knew that we can't test these, at least for this architecture, so strictly. And finally, we also tried a 32-bit version of x86 architecture, which happened to on this lowest level using special floating point unit, which executes floating point instructions. And that was pretty messy. So first of all, due to the ABI and nature of these floating point instructions, it kind of silently converts signaling nans to non-signaling nans, or these arithmetic nans. We wanted that to actually test how your implementation will respond to signaling nans if they happen to load them from memory, for example. And that was really hard to do. I'm not sure we actually fully succeeded with that. We did some workarounds, we changed the architecture of the testing tools to mitigate this issue, but mostly if you pass signaling nan value to a function, you will get non-signaling nan in the function. And the same works for returning from a function. So that's really hard to test. Secondly, and this is already something that breaks the compliance with the WebAssembly spec, is that this FPU unit operates on higher precision that you expect. I mean, it operates how it says it will operate, but it actually operates on higher precision that is required by WebAssembly. So by default, it uses special extended precision, which is 80-bit long. And only when you see the results, or you store it somewhere else, it will convert and round your results. And this happened to be actually a problem for 64-bit types. Because then rounding actually, even because you execute the instruction with higher precision, it may happen that the results will be rounded differently that you would do with going with lower precision of 64 bits. Apparently, there is a way to ask the CPU to change the precision of FPU. I don't think I'll ever succeed doing this, although some say it's possible. But it mostly means, but in default settings, this 32-bit x86 architecture is not compliant with WebAssembly. So we did found a solution, or maybe a workaround. So you can ask your compiler to actually not use FPU and use SSA 2 instructions. There are options to do that, and then you will be fine. But means you don't really have an option if your compliance is really important to you to target hardware before year 2000. And finally, the most complicated, the most wild thing we discovered. So it's something that I'm not sure the WebAssembly mentions a lot, WebAssembly spec, but it's the rounding mode of the floating point instructions. That means the rounding mode your hardware is operating on. So WebAssembly spec expects single rounding mode, which is round to nearest, or round to even, or round to nearest even, depending how it's called. It means the same thing. And not really going into details. It will, yeah, if your result, mathematical result needs rounding to some representation, it will pick the even nearest representation to the result. It will pick the nearest one, and in case you have equal distance to two different representations, it will pick the even one. And yeah, fortunately, that's like default mode the CPU operating on, and I don't know everyone who would really want to change that. Maybe there's some like numeric algorithm things that would require this. So yeah, definitely not recommended. But still, we wanted to know what will happen if someone would be able to do that. So this rounding mode is assigned to CPU core you operate in. Operating system is able to handle different processes and make sure they run in the rounding mode they started with, and so on. And there's like software way of changing these, but it will, as I mentioned, it will change how the whole thread is operating on. So that's why we kind of investigated what's going on, in case someone will be able to do that, or maybe that can be used as a feature. So your implementation will not be really WebAssembly compliant if you change that, but maybe you want to really do this for your application. So yeah, so that's what will that affect? First, it would affect rounding in the results. That's kind of expected. But we also discovered a number of compiler bugs that relate to that. And they provide, I mean, they generate code that will give you surprising results. As an example, if you convert integer to floating point, you may get negative 0 values, which should never happen. Okay, and finally, yeah, it's a bit of summary of our small achievements. So first of all, we would be really interested in having some kind of maintained and progressive WebAssembly 1.0 spec. So we don't want to change it in terms of how the implementation should behave, but at least increase number of spec tests and maybe fix some small typos and bug and small issues. That's how we use the spec as a way of communicating between different implementations in broad Ethereum ecosystem, and I think that would be really welcome in this aspect too. So based on this, all the testing and coverage analysis we actually sent around 30 changes to WebAssembly spec and Wabbit, and we also discovered some bugs in the C++ tool chains. So one is related to this floating point rounding mode. If you happen to operate on non-default one, the code compiler generate are not really 100 accurate. And second set of things we also contributed was issues with the tool chain, and mostly instrumentation tools we use for fuzzing and other kind of tests. Yeah, so thank you for all the attention, and hope you're having fun this day and tomorrow with the WebAssembly workshop.